Hello everyone, I'm Kelechi Kalu. I am a third year PhD student advised by Dr. James Davis from Purdue University. Today, on behalf of my wonderful co authors, I'll be presenting our work, an industry interview study of software sign-in for supply chain security. We deeply appreciate support from the NSF, Cisco, and Google for this work. Before I go into our work proper, I would like to highlight the contributions of our work to the security literature and practice. Number one, this is the first interview study on software sign-in in practice. Second, we present a refined supply chain factory model reflecting diverse industry workflow, showing where sign-in ought and how it should be implemented in practice. Third, we present an empirical data on organizations' sign-in challenges. Finally, we present practitioner views on the perception of the importance of sign-in and the impact of supply chain attacks and regulations on this implementation of sign-in in practice. Next, a little background to properly situate our work. First, a lot of people watching this presentation may have already seen this figure or a similar depiction of it. This is the software factory model. Software production is often visualized through this model that approximates the software engineering process as an integration of both first and third-party components, which are then built and packaged for downstream use. Technically, this combination of engineering processes and distribution forms what is known as the software supply chain. Now, the security of this software supply chain is broadly defined by three key properties. These properties have been extensively discussed in the security literature. These are validity, which ensures the integrity of the components and the actors, transparency, which maintains the knowledge of the components and the actors, and separation, which isolates components and actions performed by different actors within the supply chain. These properties are targeted by various supply chain security techniques, and a secure software supply chain needs to adhere to these properties to be considered secure. Now, provenance is a combination of the validity and the transparency properties, and it relates to the traceability of actor and actions in the software supply chain security. Software sign-in is an exemplar of provenance, and these security techniques applies the traceability factor by ensuring that the contents of the software artifacts has not been altered since it was signed. In recent years, Sigstore has become an industry-leading technology to implement software sign-in in practice and has seen widespread adoption in practice by many ecosystems like PyPI, NPM, Kubernetes, and organizations like Verizon, Autodesk, and Yahoo, etc. So, we note that the overarching goal of this research is to inform improvements in the Sigstore product as an industry-leading standard. For an effective implementation of software sign-in, there are two key components involved. One is the signature creation process, and then the other one is the signature verification process. To visualize this in practice, let's use the example of the Guava dependency from Maven Central. At the signature creation phase, Guava is signed using a private key with key ID as shown. Next, when it is downloaded by a downstream user, it is verified using the public key with the key ID also as shown. The window displayed allows the user to verify the identity of the upstream user who identifies as the person who created the package to which the package has not been altered. What then is the current state of software sign-in in practice, given its relative importance in the security of the software supply chain? Recent studies from our lab have shown the low quality of software signatures and the low adoption numbers of software signing across major open source software registries. Now, as shown in the figure showing the quantities of signature, except on registry mandation, signature quantities was always on the low side. And for the quality figure, the quality, which is the ability of these signatures to be created and verified, it mostly fluctuates, but always also on the low side, less than perfect, if I should say. Third, software signing is mostly poorly implemented in practice. In addition to this state of low quality and adoption of software signing in practice, other key points to know in the current state of software signing in practice are: one, missing or weak signing is actively exploited in real world attacks. Example is this Microsoft and Adobe attacks, where their signing infrastructures were compromised to sign malwares. The second one, which is the third on the list, is that standards and recommendations really lack concrete directions for signing in modern software pipelines. An example from the Protect Software Group of Recommendations of the NIST SP 800 as shown, which this SP 800 informs the Executive Order of 2021, is shown, and as we can see, it reads, use code signing to help protect the integrity of executable. But this does not answer the question of where and how software signing is supposed to be done in practice. It just says, do use code signing. This is kind of vague. So given the importance of signing and given the relative worrying current state that we just saw based on the implementation of signing in practice, this leads us to ask the following research questions. First, where and how is signing implemented by software teams? Second, what are the challenges that affect the implementation and use of software signing in practice? Third, what is the perceived importance of software signing in mitigating risks? And then finally, how do internal and external signing events influence the use of software signing in practice? In this presentation, I'll just focus on the first three because of time. You can read about what we did, how we did them in our full work. What did we do? So the figure summarizes our study methodology, and our study utilizes qualitative interviews to answer our research questions. And the figure summarizes the sources for our interview protocol, the structure of our interview protocol, and our data analysis approach. To describe our data collection approach, as stated, our data collection instrument was the semi-structure interviews. We utilized several sources to design our interview protocols, and we recruited 18 experienced security practitioners from across 13 different organizations. The median years of experience of these participants was 13 years, so the experience level was on the high side. The median interview lasted for 50 minutes. We summarized the demographic information for the participants of our study in the table shown. We see that our subjects reflect a high level of expertise. Most of them either implemented security controls for their organizations or they worked in security-focused organizations, making them fit to speak about security and software signing-focused questions like we had. We would also note that the asterisk sign refers to cases where subject teams built other types of software in addition to the main stated ones. The O refers to cases where subjects belong to multiple teams with other products than the one stated. Also showing our subjects' organizational demographic tables, we also see that our participants also reflect a diverse group of organizations in terms of organizational size and the product areas as shown. To analyze our data, we utilized the thematic and framework analysis methods as shown. We inductively coded the interviews and applied either one of thematic or a mix of both thematic and framework analysis to precipitate our results. Our framework of choice for this analysis was the earlier shown software factory model showing the software supply chain. We achieved saturation at interview 11. Saturation meaning that we did not observe any new main code category after the 11th interview. Invariably meaning that we did not observe any new insights from our data after the 11th interview as shown. So what did we find? To show where and how sign-in is implemented in practice, we recall the earlier software factory model that had been displayed. We modified this to first show where we expected sign-in creation and verification to be established in the software supply chain, and next, from the responses of our participants, we noted how they implemented software sign-in with respect to this modified model as we show next. First, we present our modification of the software factory model to reflect points where software sign-in ought to be created and verified by organizations. On the left, as shown on the left, we defined the points where we define the points highlighted on the right in the modified software factory model. Points marked P being points where software signatures ought to be created, and points marked by V being points where verification of signatures ought to be performed. As can be seen, while signatures are readily created, see the points marked by P, I, PE, PS, PB, and PA. They are not readily verified as seen by points marked as VI, VE, VS, VD, and VB. We shall see this fact come up in the reported challenges next. Next, to answer our RQ2, we highlight the challenges reported by our participants as hampering the implementation of software sign-in in practice. We thematically group these as either technical, organizational, or human challenges. As can be seen, there are several expected challenges like key management, lack of expertise, etc. These are expected issues from gray literature. However, there were surprising results. One, verification or lack of verification of signatures was significantly mentioned as a problem in sign-in. Participants say not much importance is given to verification, thus suggesting that sign-in is mostly used in a unidirectional way. We did not expect this as we thought the patterns shown earlier in the results of our RQ1 was not a deliberate occurrence. However, practitioners cited several issues that caused this lack of verification. One being a lack of trust in open source actors and projects, so they did not even bother to verify. And in other cases, tooling challenges to implement, or tooling rather, was also a challenge in implementing proper verification workflows. Another surprising pattern was that only subjects from large organizations talked about difficulty in operationalizing the sign-in process. We did not expect this as we thought that these large organizations have proper resources to ease this operationalization of sign-in within their workflows. So this was surprising. Lastly, another surprise, or in this case not so surprising, was that only subjects from organizations with non-security focused product areas reported a lack of management incentives as a barrier to sign-in. Next, on the perceived importance of software sign-in in practice, subjects differed on these points. The first group of practitioners saw software sign-in as crucial to provenance and integrity. This is highlighted by the quotes by subject 4 as shown. The next group of practitioners saw signing as somewhat of a secondary security technique, which they mostly said signing is important, but it's mostly had to be paired with some sort of transparency technique like attestations to be very important in practice. The final group of practitioners saw signing as mostly a requirement driven practice. So the platforms that they are building for, if they didn't require signing, they mostly kind of left it out of the picture. What are our recommendations? What are the key takeaways of our work? First, we recommend improving the signature verification workflows by improving the current tooling option. Well, this is a no-brainer since without verification, the utility of signing is really questionable. Second, we recommend at an organizational level to address incentive challenges to implementing software signing, whether this be largely on resources, mandates, etc. So, what then do we plan on doing next? Next, we are working to define what constitutes improved tooling. To this end, our work on formative usability evaluation of next generation software signing tools presents ongoing efforts to achieve this. The technical report for this work can be found in the QR code to the left, this QR code. We are also investigating the use of software signing and other provenance techniques to establish trust in the open source software supply chain uh, area. Our work in this area mainly hinges on investigating and subsequently establishing consistency in the published provenance data of software dependencies throughout the publishing pipeline. Thank you all for your attention. We have provided the full technical report for our work, which contains a full analysis, presentation of our results, our codebook, etc. That is found here to the right hand side. As mentioned earlier, we also have provided the technical report of our work, Why Johnny Signs with Next Gen Tools, which presents our efforts to improve the design of software signing tools for greater usability. Thank you very much.